Hello, everyone. Thank you very much for attending our second distinguished seminar event, which is organized by the Women in AI Committee of the AIH Institute. Today, I'm honored to present Professor Chen. Dr. Yiying Chen is a professor and department chair of electrical and computer engineering, and Peter Cheresha endorsed faculty scholar at Rutgers University. She is the associate director of Veritas Information Network Laboratory. She also leads the Data Analysis and Information Security Lab. She's a fellow of National Academy of Inventors, a fellow of ACM, and a fellow of IEEE. Her research interests include applied machine learning in mobile computing and sensing, Internet of Things, security, AI, and machine learning, etc., etc. She's a pioneer in RF Wi-Fi sensing, location systems, and mobile security. Professor Chen's contributions to the field are very extensive, and she received many awards and honors, including several Best Paper Awards, NJ Inventors Hall of Fame Innovator Award, and IEEE Region 1 Technological Innovation in Academic Award. Her research has been supported by many funding agencies and supported in numerous media outlets, including CU and IEEE Spectrum. She has been serving on the editorial boards of many IEEE transactions. Today, we are very honored to have her as our distinguished speaker. Before the talk, I would like to mention that after Professor Chen's talk, we will have technical Q&A and community development Q&A. During community development Q&A, we can have career-related or similar discussions. We will record Professor Chen's talk, technical Q&A, but not the community development Q&A. Now let's welcome Professor Chen.
Thank you. Yeah, thank you so much for the introduction. So first, I like to just introduce a little bit of WINLab, Wireless Information Networking Lab. For WINLab, it has been established for over 30 years. It is an industry university research center, and we have many PhD students and faculties affiliated with WINLab, and also every summer we have this WINLab internship that foster the research work among our undergrad students, master students, and also some high school students. And usually for the undergrad students and master students, they can be from other universities also to join Rutgers for like an 8 weeks internship program. And for the research work that we're doing, we're mainly, I have this chat screen open. It didn't block the screen, right?
What chat screen?
Yeah, so if you cannot see it,
we are good. We are good.
Okay,
Thank you. We
okay,
don't see it.
Yeah, I have it on
you.
the right hand side. Okay, thank you. That's great.
Thank you.
Yeah, so then we the most part that I like to introduce for WINLab is that we have this orbit testbed. If you see on the left hand side of the screen, you see that this is a 400 node USRP open access research testbed that the researchers from outside of the universities that they can access, that if you want, you can get an account and then you can reserve your time to do testing and to run different kinds of configurations on this test bed. And we have been working on, in addition to the core networking area, that we have been working on extending in the core networking. We're looking to millimeter wave, mobile edge cloud, for the future mobile internet, and also we're looking to healthcare IT, mobile sensing, user behavior recognition, and also we're looking to like AR, VR problems as well. So more recently, that we expand this orbit testbed under this NSF power program for $22 million support since 2018 to deploy 5G networks as testbed together with the Columbia University, New York University, and also University of Arizona. We're also working with our equipment provider, Nokia, and also service provider, Verizon, together to test in many places in New York City, including 9 large sites and 40 medium sites, that to try to test out if the wireless networking communication can provide ultra high bandwidth and low latency, and especially to support those mission critical and time sensitive applications with low latency. For example, the edge computing, future mobile internet, AR, VR, and also vehicular networking. So then I want to focus on that the research work in my area. I serve as associate director for WingLab, and meanwhile I also lead this data analysis and information security lab. And we're mainly working on this mobile healthcare, internet security, Internet of Things, and also cybersecurity and privacy. And a lot of this work we're utilizing AI, applied machine learning and deep learning to help us to perform analysis and also model construction. So just to talk about some of the impact of our work is that I listed a couple of patents that are being licensed by the outside companies. We have our patent that is the dangerous object detection using Wi-Fi signals that has been licensed to Bull Run Capital. And based on that, they set up a startup company called First Responder Technologies, and that helps to look into how to using the Wi-Fi technologies to detect in baggage concealed weapons and also the dangerous object hidden inside of luggage. And we hope to utilize the Wi-Fi as a low-cost signal approach that can make the whole system cost reasonable, and it can be deployed in many other locations, including like sightseeing places, sports stadiums, and also like theme parks. And this will serve as a complementary for this current high-end security surveillance systems, including X-ray based method approach, and also this CAT scan based method, those being deployed in the airports mostly. And we also have a patent that we called EIS that has been licensed to Aria Technologies. And Aria Technologies is focusing on how to perform motion analytics, that is to perform behavior authentication, user study, and also this motion analysis to perform well-being monitoring on healthcare using artificial intelligence. So next, I'll just quickly go over some of the projects that has been going on in my group for the past years that are related to mobile sensing, Internet of Things, and will lead to smart healthcare using AI. So for this group of projects that we have been doing is that we show that the motion sensors or PPG sensors that are being embedded in our wearable devices, for example, in smart watches, that can be utilized to help us to perform this driving behavior identification, fitness assistance, and also this gesture recognition. Or along with that, we can perform the sign language recognition by using PPG sensors. And in the bottom row, I also want to point out that those motion sensors that's embedded in our smartphones and smartwatch can actually can cause privacy leakage. That is, those motion sensor data actually including the input behaviors of the user, and that can be utilized to snoop the passcode during mobile payments. So for this line of work, we show that how the motion sensors, which is attached usually to when people wearing these devices, can help to do various kind of sensing related tasks, in addition to their original usage. And this work just further to show that when you use the PPG sensor, helps to collecting this your heartbeats that can be utilized to perform gesture recognition and further to show the to derive the sign language information. Okay, and this part is the work that we show that how we can utilizing RFID. Okay, when we have the RFID attached to human body, we can build this we call the RF Kinect that can be utilized in the exercises and also in the game domain. Is that the good thing is that the RFID is very lightweight. It can be attached to human body or to clothes easily, and it does not being affected by the lighting conditions. And along that line, in addition to what I have introduced, you see that the motion sensors and also RFID tags, they all require attachment to human bodies in different ways. And when we're looking into the things, okay, these days you have wireless signals around us. So what we like to see is that when you have wireless signals around us, the main purpose is to perform communication at device onto the internet. But in addition to that, when you have human body walking around in this wireless environment, it can actually to open a new direction of sensing. And especially we call it as device-free sensing or call it as a contactless sensing. So why is that? Okay, for what we see here is that you like in our home, right? You can have like smart TV, smart refrigerator. You also have laptops, touchpads, and smartphones, and all of this actually have already have the wireless signal communication capabilities. And by looking at that, you do not need a human to carry any devices. What it can help you to achieve is that by just human working around in this environment, this can help us to conduct different kinds of activity recognition and further to perform well-being monitoring, and then further along to achieve a smart healthcare using wireless signals. So for this slide, I show that in our earlier work, we show that how we can utilizing the wireless signals around us that can help us to perform this location-oriented activity identifications. So when we say location-oriented, okay, one part is that it's like the walking activities, and also for those in-place activities like when you are taking a phone call or you are washing dishes in the kitchen. So this can be very helpful when you have in the elderly home environment, or some people they live alone, without break their privacy concerns, without installing any cameras, but just using the wireless signals around those people, you'll be able to determine if they have an active lifestyle or they have a sedentary lifestyle, or for some people, they may have the early sign of depression because they haven't been actively moving around in their house, or they didn't eat much, or they just sleep on their bed, or they were like watching TV too much. So it can be served as an early sign of depression. So if we take a step back, right, when we talk about we turn the Wi-Fi from the communication domain to the sensing domain. Okay, what does it mean here? So when the Wi-Fi performs as the communication, okay, there are Wi-Fi packets being sent between your transmitter and the receiver continuously. And then you have Wi-Fi, the channels, the communication channels that being divided. And then so that the users, multiple users, they can communicate at the same time. So, and we understand that Wi-Fi signals that can be fluctuated when you have movement inside of the environment, especially the Wi-Fi communication is being affected by the furniture setup, by the wall setup, and also further along by the human work around in the environment, because the majority part of our body consists with water. And when the Wi-Fi signals hit to the human body, it will get reflected and also refracted and absorbed in certain parts. So the early applications for Wi-Fi signals is that people can utilizing that to for the reflection in the environment can perform localization. Okay, so that is early usage of Wi-Fi signals. That is mainly depend on the received signal strength. And received signal strength usually we only have one value in per Wi-Fi packet. So we call it as the coarse-grained information that we have. And move along, okay, we find that Wi-Fi actually suffered. One is that as you move away from the transmitter, your signal will get degraded. So you can see that sometimes when you're close to the access point or you're away from an access point, the signal strength bar in your smartphone will change, right? So this indicates that Wi-Fi signals are very sensitive to the distance from the transmitter to the receiver. And also, it can suffer from multipath environment. So what does that mean is that when Wi-Fi signals, when they hit into obstacles, when they have furnitures and human bodies, it will get reflected or passing over refraction. And then finally, okay, you will have multiple paths from the transmitter to the receiver. Okay, the signal will get into the receiver. Okay, for the sensing part is that we actually rely on this multipath effect heavily, okay, to help us to figure out, okay, what has been in the environment. And even along with looking into what are the activities being performed by human body in the environment. So more specifically, we're looking into this channel state information. Okay, the channel state information that can be extracted from Wi-Fi packets, and especially for each Wi-Fi packet, you can obtain multiple channel state information. For example, for certain equipment we talk about later on, you're going to get 36 subcarriers of channel state information in just one Wi-Fi packet. So this shows that it is a fine-grained signals that you can take a look. And in this channel state information, it consists of both the time domain information and also frequency domain information, and it has its amplitude and phase that you can study. Okay, so if we're looking into this channel response, right, the channel response, we find that those signals, okay, can provide many information of the small scale multipath channel information. And then we look into, especially we can look into amplitude, phase, and time delay. Okay, this can help us to determine what is going on. Okay, what is going on that in the environment. So, but without disclose the privacy of the human, from the human body that is being going around or going through in the wireless signals. So if you think about this, like this kind of solution, okay, it can be low cost. It is low cost, and also it can obtain the tracking information, monitoring information, but without disclosing the private information, the sensitive information. So some of the equipment that we have been using, okay, one is that we call the Intel 5300 chip that we utilizing a regular Dell laptop, and then it can help us to get the subcarriers. Like for each packet, we can get 15 or 30 subcarriers, and it's running in the regular Wi-Fi frequency band, 2.4 gigahertz and 5 gigahertz. Yeah, and also there's another part of equipment that we can use is we call this Atheros CSI tool. It comes with Atheros card and can be utilized also to do this extraction for this channel state information. So yeah, for the Atheros card, okay, the available subcarriers is 56 or 114 And also, it's also operating at the 2.4 gigahertz and 5 gigahertz test band, frequency band. And more recently, we actually make this, can extract the CSI channel state information from smartphones. So that actually will help us to move this Wi-Fi based sensing to a new altitude. So now if we're looking at, okay, one topic, okay, I'd like to focus on is that we show that how we can utilize Wi-Fi signals to perform personalized fitness assistance. So we see that, okay, these days, people after pandemic, many people are used to Zoom, attending the Zoom meetings and also work from home, working style. So people are sitting there for a longer time comparing to before. And but many people, okay, although they're very busy at work, okay, they still want to do some exercise. Okay, probably they just do some exercises, do the stretching, and do some kind of exercise in just in the home environment or like in the or in your office, okay, instead of going to the gym. So by looking at that, okay, whether it's possible, okay, we can ensure that we are doing some stretching at home or doing some heavy lifting at home. Okay, whether okay you are doing it in a correct way, you're doing it in a affordable way, and so that you achieve the exercise goals you have instead of hurt yourself. Okay, so what we'll look at is that we want to see that, okay, by using the Wi-Fi signals, okay, whether it's possible, okay, that can help people to track their workouts, even if they do not have a personal trainer at home, and even they follow on some of the personal training programs in their smartphones, in their laptops, but they still need to know, okay, whether they are following the plan and whether they perform the exercises according to the videos that they have been seeing. Okay, so the idea is that we examine the channel state information, and the channel state information actually provide very good repetitive pattern information. So if we look at this is some of the preliminary work that we show here, is that you have this. This is just in the time series, and this is the amplitude of CSI, and you see that when someone is just typing in front of their computer and then they work a little bit, then they perform some workout, right? And then they walk back to their working area and then started typing in front of the computer, right? And we see that there are some patterns that we can take a closer look. Okay, so if we do, okay, certain kind of a study for the previous results that we, preliminary study that we look at, you can see that if we perform, okay, noise reduction and also offset removal, we'll be able to see that more and more repetitive patterns are being shown here, okay, and especially later on, okay, when we convert, okay, for example, if we convert it into the frequency domain, if we convert it into the frequency domain, what we can see over there. So this shows that the spectrogram, okay, the spectrogram of the some of the just remove this part so I can see this part. Yeah, so we'll see that, okay, this is the part is that when we show it in this power spectral density, that is in this frequency domain, okay, what it shows that when someone is doing repetitive exercise, for example, you see that, okay, gradually you will see that there are 4 groups of repetitive work here, okay, repetitive workout here. There are 4 groups of them, and each group, okay, has 5 repetitions. So this is something, okay, that we're looking for, and I think this can help us, okay, to understand, okay, what a human is doing under these wireless signals. So, and further along, okay, we like to also differentiate different individuals, because sometimes, okay, even in a family environment, I will have a common living room that we have same family members, they're going to go there biking and to do some weightlifting. And also for colleagues, if we have a small workspace, in a workout space that it's possible different colleagues, they can share the same space to do the exercise. So what we do is that we're looking to build a deep learning based solution. That is, in this case, there's two simple layers that we have. And one layer, okay, is help us to do this workout interpretation. Okay, and then you also have the layer help us to do the individual identification. So based on the behavior, okay, the individual identification is more based on the behavior patterns, because even for the same kind of workout, for example, biking exercise, the same bike, when different people ride on the bike, the patterns are different. The leg gestures and also the intensity and also the way that the position of the legs are all different, and all of this will affect the wireless signals. So by looking at that, okay, we'll be able to, based on this, we can do this behavior-based individual identification and then perform a workout interpretation. Yeah, and then, okay, we also would like to say that, okay, how we can determine the, for example, the start and ending of a particular repetition. So what we look at is that usually, okay, when you, for example, just using the example of that you try to raise the dumbbells, right? So you have these two different kinds of contractions. One is we call the concentric contraction that cause your muscle to shorten and generating force to push forward, to push along, or to push forward, or to push up. Well, it also has an eccentric contractions that will cause your muscle to elongate, generating an oppositing force. So this is when we take a closer look of the spectrogram, okay, that will help us to determine those positions. And the importance of those positions is that it helps us to do the measurement, okay, to help us to determine if the users, they're following the plan, and also if the users, they're doing the gestures or doing this exercise workout in the correct form instead of injure themselves. So we're more looking to this, we call the work to rest ratio, okay, that help us to calculate the complete cycle of a repetition, okay, within one set. We call this work to rest ratio. And also we have this repetition tempo ratio, okay, that is also shows that at which tempo, okay, the user performs a repetition. Yeah, so among this, okay, we if we take a more closer look, okay, we look at this, the work to rest ratio, okay, it is what? It's the time duration for a certain workout, and it's versus the time duration, okay, for the rest followed, okay, by this particular workout. Okay. And then we have this repetition tempo ratio. Okay, the repetition tempo ratio, what's the ratio here? It's the time duration from initial position to a final position of a particular repetition versus the time duration from the final position back to the initial position. Yeah, so by looking at that, okay, we show some of the results that we have here. And this indicates that in the work to rest ratio, okay, if we set usually for the human exercise, what is the upper bound and lower bound, it will help us to identify, okay, if certain repetition have been completed too fast. Is it out of the upper bound? Okay. And also it shows that for the repetition tempo ratio, okay, it also shows that if there's any outliers in the data collection, and indicates that, okay, the users may need to lower the speed, okay, in certain ways, okay, either from the initial to the final position or from the final to the initial position. So this help, okay, it shows that this can help to prevent the users from getting injured by themselves during exercise. Yeah, so for this part of work, okay, we show that how we can utilizing the Wi-Fi signals around us that can help to perform this effective in-home or in the office workout. And especially we're utilizing the DNA-based system to help us to differentiate users, and also we can perform this fine-grained workout recognition. So we call this as the personalized workout statistics that we can provide for the user. And then I move on to our second topic today is that we show that whether we can do more, okay, with this Wi-Fi signals around us. So we like to look into, in this case, okay, we see that how we can utilizing Wi-Fi signals to help us to perform to check vital signs during sleep. So we understand that the sleep is very important in all aspects. Okay, if the quality of sleep is low, it will cause many problems. Okay, especially have show low energy during the work days, and also you can have high anxiety. And more importantly, it may cause or has been caused by some of the health problems. So what people usually do, okay, is that they care about their sleep quality and the sleep conditions because it's highly related to their overall health. Okay, especially we talk about this, those sleep events. What are the sleep events? Is that when people go to bed, when do they go to bed? When do they get up? And then how many turnaround they have at night? Do they snore at night? And what is the heartbeat and breathing rate at night? And one important problem we want to talk about is we call the apnea problem. The apnea problem is that when you sleep and then in the middle of the night, your breathing rate may stop for a few seconds, and then it will continue. And many people do not aware of that situation. Okay, when people suffer from apnea, when they wake up, even though they sleep for 8 hours, they still feel very tired. Okay, this is because when they stop breathing for a few seconds, that will cause less oxygen being pumped into the brain, into human brain, and also into other human organs. And if this kind of scenario persists, it causes severe problem to reduce the sleep qualities, and also it can also be dangerous. So the thing is that many people are not aware of that problem until it gets very severe, and then they need to go to see the doctor. And when they go to see the doctor, and usually the case is that they need to be put on all kinds of sensors and sleep there like for 1 night or 2 nights, so that the doctors can identify the severity of the problem. So in our case, okay, we have found that in the smart healthcare domain, people started looking to utilizing your Fitbit, your smartwatch, okay, help you to do the sleep monitoring. So you know that when you go to bed and when you come out of the bed, but and also some of the devices, some of the smartwatches can also measure your sleeping heartbeat, right? But the thing is that usually we feel that in order to find a complete picture of your health state at night, sleep quality, in addition to this heartbeat, we also need the breathing rate. We will call this as the respiratory rate. This is a very important biometer. Okay, that's need to be considered altogether. And also many people, especially elder people, they do not want to wear any devices during sleep. They are not used to wearing Fitbit or smartwatch during sleep. So that's why we are looking into this, we're trying to look into a contactless approach, okay, to help us to monitor vital signs, including a heartbeat and breathing rate at night. So the initial work was conducted by using a dedicated device, for example, using USRP and also self-assembled antennas that has been established from Dina Katabi's group in MIT. So they look into whether they can utilizing this USRP-based devices, okay, to perform, using this kind of devices to perform this baby monitoring at home, like to replacing the baby monitor, but utilizing this received signal strength or utilizing this wireless signals using the FMCW radar and the USRP, okay, to perform this baby sleep monitoring to prevent this sudden death syndrome during sleep. And along that direction, okay, in our work, we're looking to explore whether it's possible we can utilizing the off-the-shelf Wi-Fi device. Again, exploring the Wi-Fi signals, we understand that it can help us to derive human gestures. It can help us to derive human gestures can help us to derive activities. And also help us to perform fitness assistance. Now, whether we can push it to further to look into the vital signs. Okay, the difficulty part for the vital signs monitoring is that usually the breathing activities and heartbeat activities that can only cause minute body movement. So we can see that when you're breathing, okay, your chest, belly, okay, got affected. And during the heartbeats, okay, the human actually have whole body, small activities, including belly and also head. And even from some people, they extract the computer vision people, they extract this heartbeat information from this very small facial movement. So I have already talked about the wireless signals, okay, that is around us, okay, during the sleep, and that may be affected, okay, by human body. So by taking a closer look of the channel state information, whether it can detect minute body movement, we found that after we perform the noise reduction, okay, we find that, okay, if by just looking to the amplitude, okay, we find that there are clearly, okay, for certain subcarriers, there are repetitive patterns along the timeline. Okay, so here shows some videos demo videos that we show that when we perform this vital signs tracking during sleep, what can happen, right? So we have a small, okay, touchpad putting aside here, okay, and then we show that, okay, in our system, we'll be able to determine, okay, find the breathing rate and heartbeat at the same time, and especially we show that can be achieved by a single person sleep on the bed, or you have two people, okay, sleep on the bed. So along this, okay, we want to talk about is that first, we utilize the channel state information by examining the channel state information, perform data calibration. It can help us to determine the regular sleep events first, and also the environmental changes. Because a lot of times when you sleep, okay, there can be, if you sleep by a window, it's possible there are some driving vehicles outside of a window, and also either at night or during the winter time or during the summertime, the heating systems and air conditioning, they're also presenting noise in your system. So those, we look into all kinds of filters. It will help us to remove, okay, those, we call that as background noise or transient noise. Then after that, okay, we'll be able to determine, okay, when those regular sleep events, okay, including this going to bed, getting out of bed, and also changing the sleep postures. Okay, if you change sleep postures and how often you change sleep postures at night. Then, okay, we try to determine the breathing rate. Okay, it turned out, okay, it's for the breathing rate, we'll be able to look at the repetitive patterns, okay, in the time window. And the problem is that, okay, we find that sometimes, okay, there are some local minima, okay, that can cause problems. So what we do is that by looking into the medical information, okay, usually you understand when we look into this breathing peaks, right, what is the minimum distance between two neighboring peaks, right? So human maximum possible breathing rate at night, right, we have a range, and based on that, it can help us to reduce, okay, the number of fake peaks by using a verifying window based algorithm. And by looking at that, so if you look at this, okay, we have this time duration and the selected subcarriers, and you see that these blue dots are the detected local peaks, while the red curve is the referenced signal that's being collected from the commercial Neurolog respiration monitor logger. And this is the usually commercially utilized in the clinic. So we show that our results by looking to the channel state information, actually it's consistent, okay, with the referenced signal. Okay, and further along, we can perform this. We can look into the variance of the selected subcarrier to help us to obtain this. What are the subcarriers that have, okay, this kind of pattern? Okay, and the most difficulty part is try to track breathing and heartbeats simultaneously by using wireless signals. And the good thing is that we find they have non-overlapping ranges. That is the human breathing. Okay, usually it's in this 10 to 40 breaths per minute, while the heartbeats are usually in this between 60 to 100 beats per minute. So by looking at that, and when we convert into the frequency domain, okay, it helps us, okay, to determine, the heartbeat estimation, okay, at night. So some of the results that we'd like to show here is that we show that we're utilizing this Intel 5300 and also ThinkPad to help us to perform the experiments that we performed it in the lab environment and also to apartments by using different sleep postures. Okay, and the challenging part is that we're only using a single Wi-Fi link. That is, we show that in our experiment, we're only utilizing one transmitter device and also one router. So the thing is that if you're utilizing multiple transmitters, when you have multiple wireless signals around human body, your results actually will be more accurate. So we're looking to this the worst case scenario is that if you only have one wireless link, okay, across the human body. So the thing is that we can try this ideal scenario is that if you have transmitter and receiver, they're at both sides of the bed. So that's much easier to capture the wireless signal for which are affected by the user human bodies at night. And also we tried that the typical scenario is that you have a longer distance between the transmitter and the receiver. And further along, if the transmitter is in one room and the receiver is in another room. Okay, that is like if you're in a house scenario, the receiver actually is far away and you have walls in between. yeah, so we tested on all those scenarios, and the good thing is that we show that if by using this off-the-shelf Wi-Fi device, it can help us to collect the vital signs at night, and also detect small human body movement at night. So all of this can help actually to push forward for the smart healthcare environment. The smart healthcare environment is that means that you can do the sleep apnea monitoring at home with the low-cost Wi-Fi devices. So if you think your sleep patterns has problems and your vital signs have problems, then you can have this collected information and utilizing those information as the long-term well-being monitoring information and show them to the doctors when you go to see the doctors. Yeah, so the good thing for this part is that the doctors will have a tracking, okay, for a month or 2 months information of the patients, instead of just the patient go to the doctor's office, just go to the doctor's office like for 1 night or 2 to do the sleep monitoring. Yeah, and also the advantages for this is that when we track breathing rate, it being showing successful is that we can have a single person lying in the bed, or even have 2 people sleeping in the bed. So this can help us to largely generalize our approach. Yeah, so yeah, this concludes my talk. So I like to say that by looking into the networking side, Wi-Fi, of course, doing a great job in doing the communication. And in addition to that, we can turn it around to perform this we call the contactless Wi-Fi sensing to help us to move along in the smart healthcare domain. Okay, thank you very much for listening to my talk.
Thank you very much, Professor Chen. It was a great work. Thank you very much. So you can ask any questions if you have. You can directly unmute yourself, or you can put it in the chat and we can ask for yourself. Okay.
I have a question.
Okay, sure.
Sure. Professor, thank you for your talk. My question is that your work is based on assumption that we can get the channel state information from the off-shelf Wi-Fi device. But we know that the channel is large, so sometimes the off-shelf Wi-Fi device can only give us the compressed channel. So I'm wondering if your work use the full channel state information or compressed channel state information.
Yeah, currently at this time, we by looking into this the 2 types of chips that we've been working on, this Intel 5300 and also Atheris card, we'll be able to get this detailed channel state information. Yeah, but just as you said, not all the wireless card can provide you this detailed, this fine-grained channel state information.
So if you encounter the compressed channel information, does it still apply to your work, or how do you address it?
If you look into this compressed channel information, okay, one possibility is that you can expand your research domains and not just to utilizing one transmitter and one router. What you can do is that you can try to utilize the Wi-Fi signals all around you, right? All around. For example, you have laptop, you have smartphone, and also you may have a smart TV. This can also serve as the transmitters. And then by looking at that, that will also be helpful for you to extract the detailed information.
Okay, thank you.
You're welcome.
Any other questions? Okay, so I have a question. So from the privacy perspective, so you mentioned that wearables and sensors may have privacy leakage. So when you use a device-free and channel information, so do you somehow, we don't have privacy leakage here, right? Or
yeah, in this case, the privacy leakage concern is minimized. Many cases, people need to utilizing like cameras, okay, to perform this activity recognition, and also this vital signs monitoring even, but camera-based method is that people have concern of privacy leakage.
Yeah.
But when you look into this Wi-Fi signals, the thing is that they do not disclose human identities easily, and in that case, okay, it is help to protect the privacy, to the privacy concerns.
Yeah, thank you. And one other question is that have you compared your approach with the wearable sensors, the results of your approach and the wearable sensors? I mean, so you, for example, for the exercise and training monitoring, so you said that you use two-layer deep learning. So I want to know if the accuracy of that two-layer network, how is the accuracy of that network?
Yeah, this is a very good question. So what we look at is that when we have this, we actually have another work that is utilizing the wearable sensor to perform to perform fitness assistance to determine, to inference, okay, to give recommendations to human exercises. So we like to say that when you utilize the wearable sensors, usually it is more accurate. Okay, but the thing is that people do not always want to wear wearable sensors, and also wearable sensors that it's more individualized, right? But for us,
Yes.
if we want just to be in a common area, how you can do that. So versus wearable and versus contactless, usually contactless will suffer, okay, from some of the accuracy degradation, but that is the direction we like to move along to, because that does not involve any activities of the user. User does not have to be actively wear devices, or the users do not need to have concern of privacy leakage.
Yeah, okay. Thank you very much. Thank you.
You're welcome.
Okay, so is there any other questions from the audience? Okay, so now we can move on to the community development Q&A. So thank you very much, Professor, for your presentation.
Thank you. So I will log off. Thank you.
Thank you, Professor.